Design of pile cap. Design aspects. The reaction from the piles under the concentric load, axial load on the pile cap is assumed equal and is determined by R is equal to P divided by number of piles. Here P is the axial load acting on the pile cap. Okay. Say if there are no moments and we have only axial load on the pile cap, then the reaction from the piles will be P divided by number of piles. Say suppose there are 4 piles, then P is the total load divided by 4 will give us the reaction that will be exerted by the pile, each pile. Okay. When the pile is eccentrically loaded or subjected to lateral loads and moments, then reaction on pile R is equal to P by number of piles plus or minus my into x divided by summation of x square plus or minus mx y divided by summation of y square. Say we want to find the reaction of this pile and we have both moment mx and my. Then the first part, this, that is P divided by number of piles, that's simple, which we saw above, my into x. This is my, this is my. So my into this distance x, that is center of this pile to the CG of the pile cap, that is x. Okay, divided by summation of distance, that is x square, right? So we have to take all distance of all the pile center up to the CG of the 40 CG of the pile cap. So square of distance of this pile plus square of distance of this pile from the CG of the pile cap, square of distance of this pile and square of this distance of this pile. So summation of this will give you summation of x square, right? Plus or minus mx into y. This is our moment mx. Okay, and this is the distance x of this pile from the CG of the pile cap. Okay, so mx into y divided by square of this distance, that is from the center of this pile to the CG of the pile cap, that is for this pile, that is take the square of this distance plus the square of this distance plus the square of this distance plus the square of this distance, that is equal to summation of y square, right? So this is how we get a reaction R for this pile, right? Now we are assuming that mx is in this direction, my is in this direction. So for getting this reaction for this pile, this will be positive and this will also be positive. For this pile, we have to take negative and negative, right? For this pile, okay, mx will be negative and my will be positive. Okay, so this will be negative, this will be positive. For this pile, mx will be positive and my will be negative. So this you have to take as negative and this you have to take as positive. Okay, so this is how you get the reactions under the each pile. Now mx and my are moments about xx and y axis. So this is xx axis, this is mx is about xx and this is y axis, my is about y, right? And x and y are the distance from y and xx. So this is distance x from y, this is distance y from xx. Okay, if the lateral load y is acting, then it will give an additional moment that is equal to v into depth of the pile cap, which has to be taken in account in respect to directions. So say suppose we have a lateral load acting over here, then this will give an additional moment. This lateral load into the depth of the pile cap will give an additional moment in this direction. If you have a lateral load in this direction, into this steps will give an additional moment in this direction, right? So that additional moment we have to take in account. Okay, the CG of the pile cap, piles and column resting on pile cap has to be kept in the same line. Okay, that is the resultant CG of this four piles and the pile cap and the column should be one. They should be in same line. Okay, then only this assumption is valid, that the load is the load is distributed equally on all piles, right? Usually the minimum distance kept between the center to center of the pile is 2.5 to 3 times the diameter of the pile. That is for when the piles are friction piles, but for different types of piles this distance varies, but this is the minimum you have to keep, 2.5 to 3 times the diameter of the pile minimum. Okay, plus the outer edge of the pile should be at least at a distance 150 mm from the outer face of the pile cap. Okay, now here we can see that this shaded portion shows the pile embedment, right? So at least all the piles should be embedded 150 mm into the pile cap. Now this shaded portion is of course added in the thickness of the pile cap, but is not taken in account for the design of the pile cap. Okay, so this distance, this depth D, which should be at least 300 mm, okay, for in case of pile cap, because pile cap are to be kept rigid so that the load coming from the column are distributed uniformly to the piles. So this D should not be less than 300 mm, and this is the depth which will be used for the design of the pile cap. The pile cap is the piles are assumed to be pin jointed with the pile cap. Okay, these are assumed to be pin jointed, so this will have only reaction and no moments. Pile cap is considered to be rigid with minimum percentage of steel equal to 0.25%. Okay, now let us take a problem. Design a pile cap for RCC column of size 300 by 500 carrying a factor load 3000 kilonewton. Okay, factor moment mx 75 kilonewton meter, factor moment my, this is my, 35 kilonewton meter, a lateral load of 35 kilonewton acting in along y direction as shown in figure. Okay, the use please use M25 grade concrete and Fe415 steel. Take effective cover for the pile cap as 75 mm. The diameter of the pile is 500 mm and the pile cap is supported on 4 piles as shown in figure. Okay, so the pile cap is supported on 4 piles, so that is pile 1, pile 2, pile 3, pile 4. These are the reactions from the pile R1, R2, R3 and R4. This is the lateral load acting over here along y axis, so this will give an additional moment which will be added to mx. Okay, now let us move forward. P is equal to 3000 kilonewton, mx is 75 plus additional moment due to this, that is 35, and we are assuming the depth of the pile cap is 1 meter, which is on higher side. Okay, but we are trying to be a little bit conservative, so we are assuming the depth of the pile cap is 1 meter. Okay, so mx is equal to 75 plus lateral load into depth of the pile assuming 1 meter, that is 75 into 35 into 1, that is equal to 110 kilonewton meter. So now we are taking total mx as 110 kilonewton meter. My is given to us, that is 35 kilonewton meter. So now we can find R1, R2, R3, R4 by using this formula as we just understood above. So R1 is found to be 798.334, R2 is found to be 775, R3 is found to be 701.66, and R4 is found to be 725 kilonewton. Okay, so this is R1, this is R2, this is R3, and this is R4. Okay, so after finding the reactions, okay, so I hope I made this formula very clear. Okay, let me explain it once again. Let me take R1. Okay, P is 3000, number of pi is 4, my is 35, okay, into y. So we're taking this pile, we are trying to understand that how do we find the reaction for this pile. So this is y, right? So y is 0.75, so 0.75 divided by sum of x square. So x, this is x, this is x, this is x. Okay, so x square of the square of this distance plus square of this distance plus square of this distance plus square of this distance, that is 4 into 0.75 square, right? Now similarly, mx into y, mx is 110, y for this pile is 750 mm, that is 0.75 meters, 0.75 divided by sigma y square, right? So y, this is taking the distance, square of the distance of this pile from the CG of the pile cap, that is 0.75 square, 0.75 square, 0.75 square, and 0.75 square. Okay, summing all this 4, we get 4 into 0.75 square, right? So this is how we get this 798.33, and only thing is that you have to change the sign as according to the location of the pile and the direction of the moment, right? Fine. Now we know in case of pile cap we do not provide shear reinforcement, and the depth of the pile cap is governed by shear criteria. So the first step is that we have to assume the depth of the pile cap. So as we know, the depth of the footing is governed by shear, so let us assume the depth of the pile cap using one-way shear criteria. Assuming the critical section for one-way shear at a distance d, which is assumed to be passing over pile R1 and R2 as shown in figure below. Okay, pile R1 and R2. This is pile 1 and pile 2. Okay, these are the reaction R1 and R2. Okay, and assuming the percentage of steel, tensile steel, equal to 0.25, then the corresponding permissible shear stress for M25 grade concrete, that is tau c, is equal to 0.36 Newton per mm square from table 19 IS 456/2000. This is the critical section for one-way shear, okay, which is taken at a distance d from the face of the column. Now we are assuming that this section falls somewhere on the pile 1 and pile 2. Okay, now one important point which is to be understood over here, that if this section had fall over here, then the reaction would be 0. Okay, that the shear force would be 0. Now if this section had fall over here, then the reaction will be R2, right? That it will carry a full value of the reaction, that is R2. So shear force will be equal to R2, right? But if this section falls in between these two, then we have to find the ordinate, okay, and that will be your shear force. Okay, so we have two equations. Okay, one we know, V allowable is equal to tau c into V into D. This is B and D is the effective depth, right? Another equation we can get is V actual is equal to R1 plus R2 C1 plus dP minus D divided by dP. Okay, so how do we get this, right? Simple. You have to find this ordinate. Okay, so drawing the straight line and finding this ordinate. Okay, this is equal to, this ordinate is equal to R2 in bracket C plus dP minus D divided by dP. C plus dP. Okay, this is C, this is dP. we want to find this distance, right? So this is C plus dP minus D, that will be this distance. So this gives this distance divided by dP. dP is the diameter of the pipe, right? Into R2 will be this ordinate. Okay, so this is for R2. Similarly, same formula will come for R1, right? So this will become R1 plus R2 into C plus dP minus D divided by dP. So this is your equation 2. Now, assuming that V allowable is equal to V actual, because V actual cannot be greater than V allowable, right? Because we are not providing shear reinforcement, so V actual cannot be greater than V allowable. Okay, so assuming that V allowable is equal to V actual and equating this to equation, we get this, and solving this we get effective depth is equal to 593.76 mm. Now let us assume the effective depth equal to 600 mm. Okay, so the overall depth can be taken as effective depth plus effective cover. Effective cover given to us is 75 mm. This is 600. So overall depth for the pile cap is 675 plus 150 mm pile embedment. So gives us the total thickness of the pile, that is 825 mm. Okay, so let me show you in the figure. Okay, so this is the overall depth of the pile 675. This is the effective cover 600, that is up to the center of the bottom bar. Okay, that is D. Okay, and this is top bar. Okay, and the effective depth for this bar will be D minus 20 mm. Okay, we'll see this further, because we are taking 20 mm in design. This bar is 20 mm dia bar, and this bar is also 20 mm dia bar. From that we get this D minus 20. We'll see this later. Okay, just try to understand that this is the overall depth of the pile cap 675. This is 150 mm is the pile embedment. Okay, so total thickness will be 825. Okay, 825 mm. Right, now let us move forward. Okay, now after assuming the depth, now the next step is for check for the punching shear stress, right? So from one way shear we assumed the effective depth equal to 600. Now we have to do whether this section is found to be okay in case of punching shears or not, right? So we know that punching shear section is taken at a distance D by 2, that is 300 mm, because D is 600, 300, 300. Okay, so we get a section like this, right? Now we can see that the section falls inside the piles, right? This section does not fall on the piles, so that is why the total shear force to be taken acting on this section will be R1 plus R2 plus R3 plus R4, right? So V punching will be R1 plus R2 plus R3 plus R4, that is equal to 3000 kilonewton. The peripheral length of this section is, this is 300, this is 300, this is 500, so that is equal to 1100 mm. This is 300, this is 300, and the width of the column is 300, so this is 900 mm. So 900 plus 900 plus 1100 plus 1100, that is equal to 4000 mm. Now a question comes in our mind that if this section had fall on this pile, then how would we had calculated the punching shear? So let us take an example. Let me show you, and let me explain it through a figure. Okay, this is our these are our 4 piles. Assuming that the critical section for two-way shear was falling on the piles, right? Then this shaded portion will only be the cause for the shear force, okay, acting on the critical section, that is D by 2 at D by 2, right? Now say this shaded portion is say 75% of this total. Okay, this is R1. Then the reaction which we have to consider from R1 will be 0.75 R1. Again, say this is 75% of the total area, then the reaction from this that is to be considered will be 0.75 R2. Similarly for this 0.75 R3, similar for this 0.75 R4. So this will give you V punching, okay, which will definitely be less than which we have which we are getting at present for the our example, right? Because the in our case the punching shear critical section does not falls on pile, okay, it falls inside, so we have to take the total reaction, right? So we that is what we have done. We have taken the total reaction R1 plus R2 plus R3 plus R4. Okay, so that is how we got punching V punching as 3000. Okay, rest of the thing remains the same. That is tau V punching is equal to V punching divided by L0 into D. L0 is 4000, D is 600. So this is equal to 1.25 Newton per mm square. Permissible punching shear stress as per clause 31.6.3 IS 456-2000. Tau c two-way is equal to Ks into tau c, by Ks is equal to 0.5 into beta c, which should be less than equal to 1. Beta c is shorter side by longer side of the column, that is 300 by 5 divided by 500, that is equal to 0.6. So Ks is equal to 0.5 plus 0.6, that is equal to 1.1, which is greater than 1. So we will have to take Ks as 1. So this is 1. Okay, now tau c is equal to 0.25 under root fck. Our fck is 25, so this is 1.25. Now as tau v is not greater than tau c, okay, so our section is safe in punching shear stress. Okay, if any of this shear check, that is one way or two way, had found to be not okay, it means if this tau v was found to be greater than tau c, and then in that case you will have to increase your effective depth. But in our case it is found to be okay, so let's move forward. Now the next check which we have to do is check for punching shear stress around the pile for the maximum reaction. So maximum reaction is R1 over here, that is 798.33 kilonewton. D is 600. So we have to take a section at a distance d by 2. This is the critical section for the punching shear stress. Out of this, only this length is taking active part in taking the punching shear stress, right? So the first step is we have to find this peripheral length. Okay, so first what we do, we are finding the total peripheral length, that is 2 pi r. R is d by 2 plus 250. This is d by 2 plus this is 250 into 0.5, because we are taking only half the periphery, right? Because this periphery is only going to be active in taking the punching shear stress. So total peripheral length active in taking the punching shear stress will be 1327 mm, right? Now R1 we know that is reaction from this pile 1 is 798.33 kilonewton. So tau v punching is V punching divided by L0D, that is equal to 0.77 Newton per mm square. Now permissible punching shear stress as per clause 31.6.3 IS 456-2000. Tau c 2a is Ks into tau c. Ks is equal to 0.5 into beta c. Beta c for circular section is taken as 1. So Ks is equal to 1.5, which is greater than 1. So Ks we will be taking as 1, because Ks cannot be greater than 1, right? So Ks is 1. Now tau c we know it is 0.25 into under root fck. Fck for piles is 25, so this is equal to 1.25. Now tau v is 0.77, which is less than 1.25, so the section is found to be okay, right? Now After doing the complete check for the one-way and two-way shear, now the next step is that we have to find the tensile reinforcement, that is flexural reinforcement. Okay, the critical section for finding the flexural moment is at the face of the support in either direction. We will take additional 50 allowance of tolerance also in consideration. That means in practical field, okay, in drawing we know that the distance between the two pile is 1500 but when executed actually on site, there are chances that this distance may not be maintained exactly. Okay, so for that what we do, we take a 50 allowance of tolerance, right? So that we will consider in finding the moment. Okay, so the critical section for finding the moment is at the face of the support. So we are taking this face and this face, right? So first we will find the moment about y, right? So this moment, so we'll take this direction, right? So the distance between this section at the face of the column and the center of the pile is 600 okay, so we will have two moments, one moment from this pile 1 and another moment from this pile 4, right? So we are taking this distance as 600 plus 50 tolerance, right? So that is 650 into r1 plus r4 into 600 plus 50 tolerance. So this is how we get my. My is found to be 990.16 kilonewton meter. Now once we get this my, so we have to check for the effective depth. So this is the formula we know. From this formula we get required minimum required D, effective depth D is 353.25, but we have provided 600 so we have provided more, so it's okay, it's fine, it's safe, and the section is under reinforced, right? So once we know when the section is rectangular and under reinforced, we can use this formula for finding the AST required. Okay, this is very well-known formula. Our D is 600 FCK is 25, Fi is 415. So AST required is found to be 4856.77 square. Corresponding percentage of steel is 0.352. We had assumed 0.25% steel in case of one-way shear, okay, for assuming the effective depth, but we are going to provide more than 0.25, that is 0.352, so it's okay and safe. Okay, right, fine. So let us find the spacing. We will be using 20 dia bar as main steel. Okay, so this is the area for 20 dia bar. So spacing required is 148.69. We will provide 20 dia bar about 145 center to center along x-axis, right? Along x-axis. So steel will be provided in this direction, right? This is your bottom steel in the bottom mesh. Okay, so let us see in the detail. Okay, so this is your steel, bottom steel, that is 20 about 145 center to center. Now the anchorage to this steel, okay, should be greater than the development length for a 20 dia bar in tension, right? So the development length for 20 dia bar HYSD bar in tension is 806 when your concrete grade is M25 and steel is Fe415, right? So this is the minimum that you have to provide. We are providing more than that. Our pile diameter is 500 plus 100 this, so this is 600 plus our effective depth is 600, so we are providing 600 plus 600, that is 1200 that is much greater than 806 so it's safe, right? Fine. So we have already satisfied the anchorage length also. Now moving forward, now we will see moment in x direction, right? That about x direction, moment about x direction. So that will be that moment will come in picture due to reaction R2 and R1. So this distance is 500 plus 50 allowance tolerance. Okay, so that the distance now we will take as 500 plus 50 into R2 and 500 plus 50 into R1, right? So that is what we have taken away. R1 into 500 plus 50, R2 into 500 plus 50. The moment is found to be 865.33 kilonewton meter. Finding AST. Okay, over here the D which we have to take is 600 minus 20 mm. Okay, because this is top still, right? Okay, so this is top still. So your D will be now from the center of this bar to the top, right? So this is our D, right? This is our D. So over here it will be D minus 20 mm. Okay, so that is how we have to take D minus 20. This is 580 mm, right? So our D in this case will be 580 mm. So the AST is found to be 4372.19 mm square. Corresponding spacing, we are going to use 20 mm diabar. This is area of 20 mm diabar is 165.18 mm. So let us provide 20 mm diabar about 160 mm center to center along YY axis. Okay, along YY axis. So this is along this axis. Right. Now let us see the detail. Okay. So I have shown over here 20 mm about 160 mm center to center, right? Okay. So now we have already found the tensile reinforcement at bottom. Okay. Now comes the check for bearing stresses. Okay. Transfer of forces at the column base. Okay. So this is our column, and this is the bottom of our column, and this is the top face of our pile cap. Okay, so this is the interface of column and pile cap, right? Fine. Factored compression low force at the column base is 3000 kilonewton. Allowable limiting bearing stress at column pile interface is BC is equal to 0.45 FCK under root of A1 plus A2, where this under root of A1 plus A2 is less than equal to is greater than equal to 1 and less than equal to 2. Okay, now there are two chances. Okay, one, that the column can fail in bearing or the pile cap can fail in bearing. Okay, so first taking the first case, that the maximum bearing stress that the column can take, okay, before failure is, right, for column face FCK is 25, that is given to us, and under root A1 plus A2 will be taken as A1 and A2 in this case will be the same, right? We have to take the area of the column, right? So 300 by 500 and 300 by 500. So this value is going to equal to this value is going to be equal to 1. Okay. So FBC is equal to 0.45 into FCK. 0.45 into FCK is 25, and this is 1. So this is equal to 11.25. Now second case, that if the we'll check we will find the bearing stress which the pile cap face can take, right? So FCK is equal to 25, and under root A1 divided by A2 over here, you have to draw a frustum over here, right? That is vertical taking equal to 1 and horizontal taking equal to 2. So you will get a frustum in the pile cap. Okay, so this L into W will be your area A1, and this B into D will be your area A2. Okay, put this value over here. A1 is 2300 into 2300, A2 is 300 into 500. So putting this value over here, we find that this is found to be greater than 2, but code says that we cannot take this value greater than 2, so we'll take this value equal to 2, right? So our FBC in this case will be 0.45 into 25 into 2, that is 22.5 Newton per mm square. Now we have to take FBC equal to list of these two, this and this. So list is 11.25, so we will take our FBC max as 11.25 Newton per mm square. Okay, so whatever the actual bearing stress comes out should be less than this, otherwise we will have to provide doubles to transfer the additional load to the footing, right? So FBC actually is P divided by column base area, that is 3000 kilonewton divided by 300 by 500, that is 20 Newton per mm square, which is found to be greater than the allowable, right? That is maximum 11.25. So now what we have to do, we will have to provide doubles to transfer the additional load from column to the footing. So what we'll do, we'll extend all the bars of the column into the footing with an appropriate development length, that is LD. Okay, now so this will help in transferring the additional load from column to the footing, right? So this will become this will make the section safe in bearing pressure, right? Okay, now the next check is transfer of forces at the pile and pile cap interface, that is at this phase, right? We know that the maximum reaction coming is on pile number 1, that is reaction R1, and that reaction is 798.33. We know FBC maximum is 11.25. Actual FBC is equal to R1 divided by area, pile base area. Okay, so pi by d square is the base area of the pile. R1 is known to us, so this is 4.097 Newton per mm square, which is less than FBC max, so it is safe in case of uh, transfer of force between the pile and the pile cap interface. Okay, fine. So this is how we did all the required checks for the pile cap, and now we'll see the reinforcement detailing. Okay, reinforcement detailing as per SP34, as per clause 6.9.4.2 SP34, to avoid failure in bursting, provide 12 mm dia about 150 mm center to center reinforcement running around the pile reinforcement as shown in figure below. Okay, code says that you have to provide reinforcement running around the pile reinforcement like this as shown over here, which is shown over here. Okay, this blue lines, right? That is, this should be provided with at least 12 mm dia bar with a minimum spacing of maximum spacing of 150 mm, right? So I am providing this reinforcement around the pile reinforcement, okay, at 12, that is 12 mm dia, about 150 mm center to center. So okay, so this distance I am keeping as 150 mm center to center, and the dia of this bar is 12 mm. Okay, now at top also we will provide reinforcement, that is at least 50% of the steel that provided at the bottom has to be provided at the top. Okay, so this is at 145, this is at 160, so we are providing 20 mm, about 300 mm in both the direction. But please remember, the steel area of this both that is in x, along x-axis and along y-y, should not be less than 0.12% of the overall section of the pile cap, that is 0.12 into BD, right? Capital D, this is overall depth. Okay, both top bottom steel should have anchorage greater than the development length of the bar in tension, which we show. We already provide the minimum development, the minimum anchorage required is 806, but we are providing around about 1200 mm, so it is greater than required, so it's safe. Same thing should be followed over here also for the top reinforcement also. Okay, so which we have satisfied, so that's fine and okay. Now below portion of 150 depth is the area of pile embedment and is not considered in the design of the pile cap, right, which we have already studied. This below bottom area, that is 150 in which the pile is embedded, is not considered in design of pile. Okay, it is just considered in the thickness of pile but not considered in the design of pile cap, right, sorry, pile cap. Okay, right. So that is very important. And hard base of 100 thick PCC at least is provided below the pile cap. It is necessary, right? So this is how we do the design of pile cap. Please visit a website mmsprogramcivil.com for PDF and video for this file. I hope you must have found this video useful. Thank you.